When electrical current passes through a heating element, electrical energy is converted into thermal energy. This transformation occurs because electrons, which constitute the current, move through the element. As these electrons travel, they collide with the atoms that make up the element's material. These collisions cause the electrons to lose some of their kinetic energy. This lost kinetic energy is not destroyed. Instead, it is converted into heat, increasing the thermal energy of the heating element. It's crucial to understand that while energy is being converted from electrical to thermal form, the electric current itself is not being consumed or reduced. This is why the return current on the grounded conductor is essentially the same as the supply current. The principle at play here is the conservation of charge. In a closed electrical circuit, the number of electrons entering the circuit must equal the number of electrons leaving the circuit. Think of it like a closed loop where electrons are continuously flowing. They carry electrical energy from the source, deposited in the form of thermal energy at the heating element, and then return to the source to pick up more energy. The electric current is simply the flow of these electrons. It's the carrier of the energy, not the energy itself. To further clarify this concept, consider a simple electrical circuit consisting of a battery, a switch, and a resistor. When the switch is closed, the battery provides the electrical potential that drives the electrons through the circuit. These electrons flow from the battery through the switch and then through the resistor. As the electrons move through the resistor, they encounter resistance to their flow. This resistance is caused by the atoms within the resistor material colliding with the flowing electrons. These collisions impede the electron flow and, as a result, the electrons lose some of their kinetic energy. This lost kinetic energy is converted into heat, which is dissipated by the resistor. After passing through the resistor, the electrons continue their journey back to the battery, completing the circuit. An important point to note is that the electric current, measured in amps, remains constant throughout the entire circuit, even though the electrons lose energy as they pass through the resistor. This consistency in current is a direct consequence of the law of conservation of charge. The number of electrons entering the circuit at the battery is exactly equal to the number of electrons returning to the battery after passing through the resistor. The energy that is converted into heat in the heating element is the electrical energy carried by the current. The current itself is merely the carrier of the energy. You might ask, if the current remains the same, what actually changes when energy is converted? The answer lies in the electrical potential energy of the electrons. When the electrons leave the battery, they are at a higher electrical potential. As they pass through the heating element or resistor, they lose some of this potential energy, which is converted into thermal energy. When they return to the battery, they are at a lower electrical potential. The battery then restores their potential energy, allowing them to continue flowing through the circuit. To illustrate this further, consider an analogy with a water pump and a water wheel. The water pump is like the battery, providing the potential energy to the water. The water wheel is like the heating element or resistor, where the water's energy is converted into mechanical energy. The water flowing through the system is like the electric current. The pump raises the water to a higher level, giving it potential energy. As the water flows down to the water wheel, it loses potential energy, which is used to turn the wheel. The water then returns to the pump to be lifted again. The amount of water flowing through the system remains the same, but its potential energy changes as it passes through the water wheel. In the same way, the electric current remains the same, but the electrical potential energy of the electrons changes as they pass through the heating element. It is important to differentiate between current and energy. Current is the rate of flow of electric charge measured in amps. Energy is the capacity to do work, measured in joules. Voltage is the electrical potential difference, which is energy per unit charge measured in volts. In the context of a heating element, the voltage across the element determines how much energy is converted from electrical to thermal form for each electron that passes through it. The higher the voltage, the more energy each electron loses and the more heat is generated. The current determines how many electrons pass through the element per unit of time. The higher the current, the more electrons pass through the element and the more heat is generated. Power, measured in watts, is the rate at which energy is converted. In a heating element, the power is equal to the voltage across the element multiplied by the current flowing through it. Therefore, to increase the amount of heat generated by a heating element, you can either increase the voltage, increase the current, or increase both. However, it is crucial to consider the resistance of the heating element. According to Ohm's law, the voltage across the element is equal to the current flowing through it multiplied by the resistance. Therefore, if you increase the voltage without changing the resistance, the current will also increase. Similarly, if you increase the current without changing the resistance, the voltage will also increase. In practical applications, the resistance of a heating element is usually fixed. Therefore, to control the amount of heat generated, you typically adjust the voltage applied to the element. For example, in a toaster, a heating element converts electrical energy into thermal energy to toast bread. The amount of heat generated is controlled by adjusting the voltage applied to the heating element. When you select a darker toasting setting, you are essentially increasing the voltage, which results in a higher current and more heat. In summary, when electrical current flows through a heating element, electrical energy is converted into thermal energy. The current itself is the carrier of the energy. The return current is the same as the supply current due to the law of conservation of charge. The amount of heat generated is determined by the voltage, current, and resistance of the heating element.